This presentation is delivered by the Stanford Center for Professional Development.
So actually, first of all, embarrassingly, I guess I have to introduce myself, even though it's the second week. So, and I have to apologize for not being here last week. Actually, for the record, I've never done that before. So I've never missed an entire first week. So, and I promise I won't miss any more classes. Maybe, mostly. Anyway, I'll make a very, if I miss any other classes, it'll be for a really, really good reason. Anyway, you were in very good hands with Jacob, so that's okay. A couple of announcements. If you go down the pad, I'll start with a bunch of administrative things. The first is that we have 2 more TAs. This is Argyrios Zymnis, who is sleeping, as most senior PhD students would be at this hour, and Kwangmo Ko is over here. So. What we'll be doing is adding more office hours, both for them. Since we now have essentially like an army of TAs, we can have. We were joking about just having office hours like 24/7. I don't think we can pull that off yet, but we're going to do something like that. And in fact, I do have some questions. Also, I'm going to add office hours for myself. And we don't know, we're trying to figure out I don't know if people have opinions about where we should distribute the office hours. So I don't know. We had our own conjectures, but if anyone has any other. For example, in my case, I might add them Tuesday and or Thursday afternoons. What do you think? Yeah. Oh, that was a yes. Oh, okay. Okay. All right. All right, fine. Then I'll do that. I'll add office hours for myself and for the TAs. Now, this week, of course, is Chaos Week, otherwise known as the EE-Quals Week. If you're not in this department, you cannot even imagine what this week is like. But just look around you, and you'll get the idea. If you're in this department, you know full well. So those office hours, at least in my case, will have to kick in next week. So. But look to the website for that. Let's see, a couple of more administrative things. Here's one. It has to do with the homework. What we're going to do is we actually did a little bit of planning for the homework, and the way it's going to work, and actually it's a good excuse for me to say a little bit about how the course is going to go for a while. And this is actually substantive. Homework 1 and homework 2. Homework 1, which you've already started. Yes? Okay. So homework 1 and homework 2 are going to be just these big, long slogs through, I don't know, you'll have nightmares about it. And people coming up to you on the street and saying, is this set convex? Is this function convex? And things like that for years. But the nightmares will subside eventually. They'll always be there to some extent. So there'll be little triggers later in your life that will set it off again. Someone will say something like, which of the following, and something will remind you of it, and you'll get all on edge. Seriously, what we're going to do is this. We're trying to go fast over the first material, which is actually a little bit, it is interesting. We're going to use all of it eventually. But it's sort of the mathematical basis of what we're going to do. And so the idea is to actually not cover it as well as we should. So meaning, we're going to go fast. Faster than there's no way you could kind of absorb every subtlety. So what we'd like you to do is read the book. That goes without saying. Read the book. You'll do the homework. Listen to the lectures. And you'll get maybe 75% of it, something like that. Actually, that's enough. Because what's going to happen then is by homework 3, it'll actually get interesting. And we'll be doing a lot of applications from then on, kind of mixed in with new material. And at that point, it gets interesting. So the idea is to avoid having something which for 4 weeks, nonstop, is essentially just a math course. So that's sort of the rationale behind this. So on your part, what it means is this. If you think we're going fast, you're right. We are. But it also means don't worry about getting absolutely everything. All the things we're going to see, you're going to get lots more chances, and it'll be more interesting later because it's going to be in an applied context. So having said that, though, this is your time to kind of get down some of the basics. Okay, so that's our plan for how the course is going to go. I should also say that there was one change. I don't know if it was announced yet, and that is that the homework we're going to try to have graded a little more seriously. Then, for example, 263. In 263, the homeworks were graded on a scale of 0 to 4, very crudely. That's nominally 2 bits. The actual amount of information, from the entropy was on the order of 0.2 bits. We haven't worked out actually what the entropy is, but it was something like that. So we're going to try to do at least give you a little more feedback and make this 0 to 10. It's going to be imperfect, but we're going to attempt that. So it's going to look something like that. The idea is if it's perfect, that's a 10. Anyway, we'll get into that later. Another admin, maybe just 2 more admin things, and then we'll move on to real material. The other is that we've posted another reading assignment, and so right now you should be reading chapter 2. And when you finish chapter 2, keep reading. Just go right on to chapter 3, and 4 for that matter after that. So, and then let's see, one more admin announcement. This is a bit specific, but it's a good excuse to mention something. We got several questions about what do inf and sup mean. So, and that's a good excuse for me to say a little something. So you are welcome, if you don't know what these mean, you're welcome to treat these as min and max. Okay? So one thing is actually for questions like that, when we get more than 10 or 15 questions, we're going to start a FAQ, an FAQ on the website. So please, sorry, it's already there. Okay, so it wasn't there 2 minutes ago. But anyway, so there's going to be a FAQ section in the website. Already pushed over? Oh, okay, so there is a FAQ section in the website. And so please check there if you have some sort of basic question first. And this is anything ranging from, I can't get this software to work to what do inf and sup mean? Or when is homework 3 due? Or I don't. I guess that's posted on the website. But that kind of stuff, we'll just post stuff there. And if you have suggestions actually for us to add stuff there, just send us email. So, okay. And on this topic, I should say a little bit. If you have had analysis, a course on mathematical analysis, then you know what infimum and supremum mean. If you haven't, I would simply substitute min and max. And the way the course is going to work is something like this. The book, by the way, is not, there are many more mathematical books. So if that's your interest, on the website, there's pointers to other books. You can go insane, and they can be as formal as you like. By the way, outside the lectures, you're happy to hunt me down. I'll tell you what I know. If this is your interest. Frankly, that's not really the whole point of this class, but I'm happy to answer any question about that. And I'm talking about things like, detailed conditions. Is this open? Is this closed? What happens at the boundary? All these kinds of things. What are the exact conditions under which this holds and things like that. In lecture, I'll be very cavalier about these things. So boundary conditions don't hold. Everything I say is modulo some technical conditions. In the book, we, generally speaking, don't lie. So if you look in the book, there's just a few things that are wrong. Well, you can treat it as true, the book. But in lecture, I'll just be happy to just go broad brush over these things. And I think the class, by the way, is just from past experience. If you have a deeper understanding of all the analysis and stuff like that, great. But I haven't noticed that it makes any difference in the experience. You don't have to know it. You can work with an intuitive idea of these things. Not really worry too much about boundary issues and things like that, and you'll be just fine and totally effective. at using these methods. So, okay, so that's all my admin stuff. Any other questions? Otherwise, we'll jump in. So today we'll cover convex functions, and let me say a little bit about how this is going to work. If you go down to that pad here, that'd be great. There we go. So we're going to look at convex functions. First of all, just define what one is, and then look at various aspects of it. And let me say operationally why you need to know this, because one of the things you're going to need to do is actually determine if a function is convex. Because to use this material, that's like the most basic skill. So that's why you want to look at all this and see how this works. Okay, so let's just jump in. Well, a function is convex if its domain is convex. That's the first requirement. And the second is that it satisfies this inequality for theta between 0 and 1. So this says that if you evaluate f at this point you saw in the convex sets lecture. This is a convex mixture, convex combination of x and y. So geometrically, it's a point on the line segment between x and y. This says if you evaluate a function at a point on a line segment between x and y, the result is actually less than the same mixture of the values of the endpoints. Or in terms of the graph, it says that if you take 2 points on the graph of the function and then draw the straight line that connects them, and I guess an old word for that is the chord or something like this, right? So that's a very old word, is the chord. And this says the chord lies above the graph. So that's what this inequality says. And you'll get a very good idea of what this means eventually. Another way to say it, I mean, just very roughly, is upward curvature. So it just means curves up. That's all. By the way, of course, a convex function can look like that. It can be monotonic decreasing. Nevertheless, the curvature is upward for a function like that. So that it doesn't have to be bowl-shaped, but it should have positive curvature. Okay. Now you say a function is concave. If minus f is convex, that means negative curvature, downward curvature, something like that. And it's strictly convex if it's convex, and not only that, but this inequality here holds with strict inequality, provide theta is strictly between 0 and 1. So that's strict convexity. And you have strict concavity too. So let's look at some examples. Well, and these are just on R. So these are just functions you can draw. So the first is just an affine function. So that's linear plus a constant. It has 0 curvature. So it's convex. And in fact, what happens for a function that's affine is the following, is that in fact you have equality here for always for an affine function. That's exactly what it means. It means that if you do a linear interpolation between 2 points, you actually get the exact function value. So that's essentially the boundary of the set of convex functions. Exponential doesn't matter what the coefficient is in here. This is convex. So if a is positive, it's increasing, but the curvature is upward. If it's negative, it's a decreasing function, but it's convex. Powers separate out. Depends on it depends on the value of the exponent. The exponent's 1 or bigger, or if it's negative, or well, 0 is that's just a constant 1. In that case, it's convex. I mean, these are things you could just draw and see. So I think the question as to whether or not a function on R is convex is a non-issue. Here's how you check. You draw it, and you use your eyeball to see if it curves up. I mean, there's really no issue there. Okay, so we'll find formal ways to verify all these. But I think in terms of a function on R, there is no issue. You draw. Does it curve upward or not? That's the question. And you have things like power of absolute value would be another one. Negative entropy is x log x. That's something that goes like this. It's got this infinite slope here, and then goes like that. Something like that. And but the point is it curves upwards. That's negative entropy. So entropy, which is minus x log x, is going to be concave. Okay. Now, concave functions examples would be like an affine function. And in fact, of course, if a function is both convex and concave, then it's affine. And that's clear because it says basically this inequality holds one way and the other. That means it's equality. This in fact implies the function is affine. Okay? There's powers in the range between 0 and 1, like square root, for example. You just draw this. It's clearly concave. Logarithm is another famous example. Okay. A little more interesting examples on Rn and R m by n. That's the set of m by n real matrices. So here's, well, of course, you have an affine function on Rn. That's A transpose x plus b. That's a general linear function plus a constant. So this is the form of a general linear function, affine function on Rn. And that's going to be convex. It's also concave. Norms. So any norm is convex. That follows actually from triangle inequality, or that's part of the definition of being a norm. And examples are things like this, the so-called p norms, which is the sum of the absolute value of xi and then to the 1 over p. Now for p equals 1, that's the sum of the absolute values. For p equals 2, it's the usual Euclidean norm. But for example, for p equals 3, it's the 3 norm, right, which is the cube root of the sum of the cubes of the absolute values of a vector. Yes?
Is there a half norm?
That's a very good question. Is there a half norm? So some people would, so let me answer it first. Well, let me just first give the answer. The answer is no, because the square of the sum of the square roots is actually not a convex function. And therefore it can't be a norm, because norms have to be, all norms are convex. It's actually concave. Now, having said that, it is currently very popular in statistics and a bunch of other areas to use as a heuristic for finding a sparse solution that involves, we'll see this later, by the way, using things like the so-called p norm for p less than 1, but it's not a norm. So it's weird.
Why all the norms have to be convex?
That actually follows from the definitions of norm. A norm has to satisfy a triangle inequality and a homogeneity property. And then from those two, you can establish it has to be convex. So, by the way, I should mention something here. It's not easy to show. If you put, just for general p, just take the 3 norm. It's not easy to show that's a convex function. It's not easy at all. So it's not hard, but you have to know exactly just the right, 5 or 6 steps to do it. So this is maybe the first thing I've said that wasn't trivial, and it's not. So, okay. Let's look on matrices. Actually, every now and then there are going to be problems where the variables are matrices. Sometimes square. Sometimes they'll be square. Sometimes they'll be rectangular. But let's look at a couple right now. One is an affine function on matrices. Well, the general form looks like this: trace of A transpose x plus b. By the way, when you see this, you should read this as follows. This, by the way, some people write this as the inner product of A and x plus b. That's the standard inner product on matrices, is trace A transpose x. If you work out what it is entry by entry, it's just this. So, it's as if, well, it's this. Let me write it another way. See if I can do this. Well, okay. If that's not totally, that's mixing weird and that's mixing notation. But the point is, this says if you string out A as a vector, string out x as a vector, and then calculate the ordinary inner product, well, you would just get this, like that. Okay? So, and that's the same as this thing. So this notation, you might as well get used to it. When you see trace A transpose B, A transpose x, that really means you can think of it this way. And by the way, another notation for this is A big dot x or something like that. So you'll see that. Okay. Here's an interesting function, which is the norm of a matrix. So that's this, and I'm talking about here the spectral norm, or the maximum singular value, or you can call it many other things. There's not that many others. Actually, there's probably just a couple other names for it. The L2 induced norm, and maybe that. Now I'm running out of obvious ones. So this is the square root of the largest eigenvalue of x transpose x. Now I want to point something out. That's a very complicated function of a matrix. Okay, so it is not a simple, to take the matrix form x transpose x, find the largest eigenvalue of it, then take the square root of that. That's a chain of quite complicated operations. So that's a function which is not simple, but it's a norm, and it's convex. Okay. Okay. Now here's one extremely useful property for convex functions. It's this: a function is convex if and only if it's convex when it's restricted to any line. That's very, very useful. And in fact, it's one of the best ways to actually establish convexity of a function. And essentially, it means the following. I already said that convexity of a function on R is a non-issue. Plot and use your eyeball. This says, in principle, convexity of any function is a non-issue. And the only hitch is you have to, unfortunately, plot and use your eyeball on all possible lines that pass through the set, of which there are an infinite number. Okay, so that's the only, but conceptually it means that somehow there's nothing subtle about convexity. It's basically if you take some complicated, horrible function in multiple dimensions and you take a line, then and then view the function on that line, you should view something that looks like that. And if that happens, no matter what line you choose, it's convex. That's what it is. So this is not too hard to show, and may indeed be coming up on a homework or something for you. I mean, to establish it, this is the case. And let's look at an example. So here's an interesting function. It's the log of the determinant of a positive definite matrix. Okay. By the way, that's a complicated function right there. For example, if x were 10 by 10 and I wrote this out, it wouldn't, it would take like a book to write out what that is, because you'd have 10 factorial terms in log det x. So this is the log of a polynomial of these 100 by, well, okay, it's 10 by 10, so there's only, 55 entries. I mean, because the bottom is the same as the top or whatever. So there's 55 entries, free variables. So this is the log of a polynomial in 55 variables, and that polynomial probably would take a book. I'm just making a wide guess. By the way, it could be a whole lot bigger than a book too. I could be off a bit. So this is really a fantastically complicated function. Actually, this function is concave. That's going to be very important. It's going to play all sorts of roles later. So let's actually show that this is concave using this technique. This is, well, it's the only technique you know, except for applying the definition. By the way, what does it mean to say it's concave? Basically says that if you have two positive definite matrices and you evaluate the log of the determinants of them, and then you form a blend of the two, let's say the average, it says the log of the determinant of that average is bigger than or equal to the average of the log of the determinants of the endpoints. Everybody follow that? So and this is not an obvious fact. I mean, once you know it, it's obvious, but, well, it's actually not obvious. Let's just say that. Even once you know it, it's obvious only because you know it. So, okay. So let's see how this works. So to establish this, what we have to do is we have to pick an arbitrary line in symmetric matrix space. Okay? So what does a line look like in symmetric matrix space? Well, it looks like this. And it's one that passes through the positive definite cone. So it's going to look like this. Without lost generality, it looks like a point, x, which is positive definite, plus t times a direction v. Now this direction v is a symmetric matrix, but it does not have to be positive semi-definite, right? Because that's a line and a direction. There's no reason the direction has to be positive. It does have to be symmetric. So this thing describes a function of a single variable t. And we have to check that this is in fact a concave function of t. So that's what we have to do. By the way, if you're looking at some function, you have absolutely no idea if it's convex or concave. First thing to do, you're near a computer, sit down, generate arbitrary lines, and plot, and look. Look at 10 or something like that. And by the way, if you find one that doesn't curve up, then you destroy all evidence that you did this, and then confidently say, well, obviously, that's not convex. Okay? And then erase all the files. It's 3 lines, but the point is then you erase the evidence. If they keep coming up like this, Then after 50 times, it's like, well, okay, here goes. And then you roll up your sleeves and you move in to prove it. It may not help you, but it's actually quite useful to do this. I've actually failed to follow this advice on several occasions, jumped in 45 minutes later, got tired, wandered over, typed in a few, quickly found a point where, it had the wrong curvature, and then realized I'd just been completely wasting my time. So, okay, I just mentioned that. Don't tell people where you learned that. Okay, where you heard that. All right, so let's work out what this is. Well, I'll write x. I'm going to write this, there's lots of ways to do it, but x is positive definite, so it has a square root. So I'll take a half out on each side, and this will look like this. T, it's going to look like that, times x half. This matrix is this. But the determinant of a triple product is the product of the determinants. And you take logs and it adds and all that. So you get this, okay? Because the log of x half plus log det x half plus log det x half is log det x. So you get this thing here, okay? It's still not too obvious. But what we're going to do now is this. I'm going to write this thing is asymmetric, but not necessarily positive. It's certainly not positive semi-definite or anything like that. You don't know. Matrix will take its eigenexpansion. We'll write this as whatever, Q lambda Q transpose, and you get this with a T there, like this. What I'll do now is I'll do the trick of writing I as QQ transpose. Then pull it out on either side, and I'll get det Q. Det Q is either plus minus 1, but it doesn't matter. And then I'll end up with det I plus T lambda. That's a diagonal matrix. I know what the determinant of a diagonal matrix is, the product of the entries, and so I get this thing. Okay? So I went over this a bit fast, but I promised I would go fast. So, yes?
How did you choose the directional matrix V?
I did. It's arbitrary. It's extremely important that it's completely arbitrary. So the technical answer to your question, how did I choose the direction V, is I didn't. Or arbitrarily, I suppose, is the actual correct adverb or whatever. Okay? That's because if I chose V in any special way, then my final conclusion is not going to hold. It's not right. To be convex has to be every line. Has to be convex when restricted to any line through the point. Okay. Now we're in pretty good shape. Because I know what log 1 plus T lambda looks like, for any real number lambda. If lambda is positive, it looks like one thing, and it goes like this. Or, sorry, it goes like that. Nope, sorry, that was from my point of view. I did it right the first time. It goes like this. If lambda has the other sign, it goes like that. Either way, curvature is negative. And so this is concave. Okay? So, by the way, this is going to turn out to have all sorts of implications. If you're in statistics, if you've taken information theory, communications, a lot of other things like that, actually if you've done any computational geometry, it turns out some things you know are actually related to concavity of log det x, things involving like entropies of Gaussian variables and things like that. So actually, throughout the class, when we've actually covered some material, you'll see all sorts of things you know from other classes are going to start to connect to various things here. Okay. Next topic is this is just a bookkeeping thing. It's quite elegant, but it's actually something good to know about. Works like this. When you have a convex function, it turns out that you can encode it's convenient to encode the domain of the function by simply assigning the value plus infinity when you're outside the domain. So if you have a function f with some domain, then we define an extended valued extension as follows. It's going to agree with the function if you're in the domain, and we'll assign it infinity outside the domain. And I mean, let's not worry about this here, but technically there's a difference between f and f tilde, and the difference occurs when you call f at a point outside the domain. If you call f at a point outside the domain, you get the dreaded, what's returned is the dreaded NID token, otherwise known as not in domain. Oh, of course, what would actually happen is something, some exception would be thrown at you or something like that. or a nan would come back or something like that. But that's what that is. Whereas f tilde, evaluated at a point outside the domain of f, simply returns the token plus infinity. Okay? So now what happens is then everything kind of works. So if you have a function, sort of that looks like that, and its domain is from here to here, that's a convex function. What we simply do is we simply assign it the value sort of plus infinity outside. Here, that's plus infinity. Okay? So it looks like that. So you make it plus infinity. Actually, everything works, including this inequality. If you take this point and this point, everything works. If you draw, everything will work. Because this line will now have slope going straight up, and it all just works. Okay. So this is just something to know about. It's absolutely standard in convex analysis. So you should know about it. Now for concave functions, it's the opposite. You encode the domain, or I should say you encode the not domain as minus infinity in the function value. Okay. Okay. Now we get to first order condition. So first of all, just to remind you, a function is differentiable if its domain is open. I mean, you can also talk about being differentiable at a point. And you'd say that it's differentiable at a point if the point is in the interior of the domain. But we'll just talk about being differentiable, period. So a point is differentiable if its domain is open and the gradient exists at each x in dom f. Actually, this is a bit circular, and what you really want to say, well, you really want to say this is not, this is informal. So I'll just leave it that way. So here's the first order condition for convexity. This is very important, and actually it's a hint as to why convex optimization actually works very, very well. Here it is. It says the following. Form that is the Taylor approximation, the first order Taylor approximation of f at x. Okay, that's as a function of y. That's the Taylor approximation. So here's f. Here is this Taylor approximation. Of course, this is drawn in R, but in general, this is the Taylor approximation. And of course, what the Taylor approximation is this. At the point at which you expand it, it's perfect. In other words, it coincides with the function. Nearby, so near x, the Taylor expansion is very near, by which I mean to say formally near squared. So it's small. The error is small squared. So what Newton tells you, or calculus tells you, is that these two functions, one is this affine function and one is this one, is that they are very near as long as y is near x. Here, for a convex function, this thing is actually always an underestimator. So that's the important part. It says that the first order Taylor expansion is a global underestimator of the function. Period. That's what it means. Now, this is actually the key to everything. I mean, once you know all these, it's kind of trivial, but this is the key to everything, because let me explain what happens. Later in the class, we'll formulate all sorts of crazy problems as convex problems. Okay? And we'll come back and we'll say, I've solved it. Here, this is the solution. It'll be some horrible, complicated problem with, hideous nonlinearities, things that are non-differentiable. God knows what's in it. And someone will say, how do you know that's the global solution? That problem is highly nonlinear. It's got all, that's ridiculous. Maybe it's a local solution. I'd believe that. But how could you possibly assert that all over R100, there's no point that does better than your point? Maybe there's some sick little region you haven't examined yet where the function miraculously does better. Everybody see what I'm saying? It's really a preposterous statement that you're making. After a while you'll get used to it, but it's preposterous. And then you said, oh no, because this is a convex problem, I assure you this is the absolute best there is. And someone will say, but how can you say that? It's ridiculous. This is it. And the reason is this. From local information, that's a gradient. A gradient is local information. It says from local information you get global conclusion, which is this inequality. So just, although the inequality is not a big deal, the fact that it says something that you evaluate a gradient somewhere, that's completely local. To evaluate a gradient, all you need to do is wiggle x around near that point and see how the function varies locally. You don't have to do any big exploration far away. What it says, if that function is convex, then from that little local exploration, you can make global bounds on that function that hold arbitrarily far away. Everybody see what I'm saying? So not a big deal, but this is, if you ever, what's going to happen is, 2 weeks into the 3 weeks into the class, things that are just preposterous will be asserted. You'll be asserting them, in fact. And if you ever wanted to go back and say, well, wait, you know how it always is, right? It's just a string of little trivialities. And the next thing you know, you've said something quite deep. And then you always want to go back and say, well, where exactly did that happen? Anyway, I say it happened here. That's what I say. OK. Second order conditions. I guess you've seen this. This you've probably seen in a calculus class or something like that. Usually it has to do with sort of this part, I forget, the sufficient conditions or checking if something's a minimum or maximum or something like that. And it basically says that it says if it's twice differentiable, it says if the Hessian, which is the matrix of partial derivatives, if that is, it says the following. It says it's convex if and only if that matrix is positive semi-definite. Okay? So that's the condition. And then there's a gap in characterizing strict convexity. And the gap says something like this. It says, certainly, if the Hessian is positive definite everywhere, then the function is strictly convex. Actually, the converse is false, and an example would be x to the fourth on R. That's a strictly convex function, x to the fourth, but its second derivative at 0 is 0. Okay? So that's a case where the second derivative fails to be positive at the origin. Okay. So this is the condition. So this is useful sometimes. Actually, this is less useful, in fact, and also although you will have to, we'll see to it, let me put it that way, that you'll have to use this method to establish convexity or something. But as you'll see later, this is to be avoided, because generally it's a pain to show something is positive semi-definite. Unless it's really simple, the function. But we can knock off some examples real quick. Let's characterize all quadratic functions right now. So a quadratic function looks like this. It's a quadratic form. So P is symmetric here, a linear function, and a constant. Okay? So the gradient of this function is px plus q, and the Hessian is p. So it's constant. It's got a constant Hessian. So a quadratic function is convex if and only if p is bigger than or equal to 0, if it's a positive semi-definite matrix. And an example would be least squares objective. That just immediately. So here the Hessian is A transpose A, and that's going to be positive semi-definite. So that's always convex. Here's a function that is not obvious. This is probably one of the first functions you encounter that is not obvious. It's not obvious that it's convex, maybe other than minus log det x. But here's one. X squared over y, just two variables. So this is convex in x and y, provided y is positive. And let's take a look at that. First of all, let's just check a few things. If you fix y, it's convex in x, that's clear. If you fix x, it's convex in y, because it's a 1 over y in that case. Okay? Now, by the way, I'm using there this idea that these are essentially lines. That's a line. One is aligned with the x-axis, one with the y-axis. So if a function of many variables is convex, it better be convex in each variable separately. The converse, of course, is completely false. You can have a function convex in each variable separately, but not jointly convex. And the answer, the distinction comes completely from the Hessian, right? So you have for example, a function of x and y, two variables. You have a 2 by 2 Hessian. That is required to be positive semi-definite. To say that it's convex in x and y, it says the diagonals of that Hessian are non-negative. That's what it means. That tells you nothing about the off-diagonals, right? So there's a further condition linking the two and the cross condition. The question?
So is there any way to prove convexity or show convexity by projecting it onto one dimension however many number of times?
But be careful, because we're not projecting onto a dimension if we're restricting to one dimension. So, and the answer is yes. In principle, if you restrict it to any line, Any sort of one-dimensional set that passes through it, and the result is always convex, then it's convex. But it has to be understood that's in principle. I mean, unless you're prepared to do something symbolic with every line, like we just did with log det. Okay? Okay, so let's take a look at this function, and let's show that it's by the way, here's a plot of it. So it looks, I don't know. Some people have told me it looks like a boat or something like that, the bow of a boat, or I don't know. Anyway, so, and if you look in, I guess one slice, it's quadratic, and I guess it's maybe, I don't know what it is anyway. So if you slice it different directions, you get obviously convex things. Okay, so let's work out the Hessian. Well, I worked it out. I'm not going to calculate in front of you all the partial derivatives of the things here. But, you calculate partial squared f, partial x, partial y, and the diagonals. And you fill it out. And you get a matrix, which indeed is rank 1 and positive semi-definite, because you write it this way. And here we're using the fact that y is positive here to ensure that this is positive semi-definite. So that's convex. So that's your... maybe one of your first non-obvious convex functions. Okay, here's another one, is the so-called log sum exp function, and that's the log of a sum of exponentials of variables. Okay, now actually before we go on, let me just say a little bit about this function. It's first of all, it's sort of like a smooth max, or in fact some people there are fields where this is simply referred to as soft max. So I know whole fields where this is universally called the soft max. The reason it's soft max is this. If you take a bunch of variables x1 through xn, then exp increases, of course, very quickly. So the biggest x is a lot bigger. I mean, if there's a good gap between x, the largest x and the next one, exp will accentuate the spread. Okay? If you add these up and then take the log, if, for example, one of the x's is kind of isolated and far away from the second, if the biggest is away from the second biggest, then you can actually quickly see that basically this sum exp is basically exp of the largest. You take the log of that and you get the largest. So this is sort of a smooth, it's a soft max, some people call it. Okay. I should also mention this is, if you're in electrical engineering, this is the dB combining formula. So this is how you combine powers that add incoherently. So if you have, for example, if you have a bunch of powers adding, and the powers come in at, minus 15 dBm, minus 22, minus 37, and minus 3 dBm, everyone in EE here knows what the power of the result is, except I forgot the numbers I just listed, but I think it's minus 3 was the largest one. The answer is it's minus 3. So whatever, that's minus 3 dB. Reference to a milliwatt. And let me explain what that is. Exp converts from decibels to power. This does incoherent power addition, and log converts back to decibels. By the way, obviously, if you're not in electrical engineering, you don't have any idea what I'm talking about, and that's just fine. So, okay. So, anyway, so I'm just saying this is a function, you've seen it before, and it comes up in statistics as well, in exponential families. This comes up all the time. Okay, so, well, statistical mechanics too. It's the denominator. A fancy version of this is some normalization constant or whatever. And I'm sure people here know a lot more about this than I do. Okay, all right. So that's a convex function. And the argument would go something like this. You take the Hessian. Now, by the way, if you're curious, no one can look at this and write this formula out for the Hessian. So if you're looking at this and saying like, oh, that looks pretty easy. Anyway, it's not. You have to sit down and first you try to find some secret rules for chain rules for calculating the Hessian of some function. That's the first thing you do. Then that gives you a headache. Then I usually just basically at some point you give up and you just go in there. You just calculate partial squared f, partial xi, partial xj. There's just no way around it. You get this huge, horrible mess. Then you have to go from your mess, your index by index representation, to a matrix representation, and then you're off and running. Then you go back and erase all that, and then write things like this. So just like this, and then that's the idea. So, but let's take a look at it and see what it says. Now, when you do this, you look at it and you see, well, there's this first term. z here is this exp of x, so it's obviously it's non-negative. This thing here is interesting. That's a positive diagonal matrix. So this is positive definite, positive semi-definite. Well, it's positive definite. And of course, what you're hoping for is to add that to something positive definite, at which point it's easy because you just say sum of two positive semi-definite matrices is positive semi-definite. Done. And there's a little minor problem, which is that the sign goes the wrong way. And that could mean two things. It could mean either this is not convex, or you have to work harder to show this thing is positive semi-definite. And it's the latter here.
Z is a vector here?
Yep, z is a vector.
What is diag of x?
What is diag of
H.
z here?
Yeah.
Oh, what is diag of z? Oh, diag of z, you take a diag. And this is actually entering, of course, it's MATLAB slang or something, okay? So, which, anyway. But it's entering, it's sort of entering mainstream mathematical notation. Exactly. Yeah, so diag of a vector embeds the vector into the diagonal elements of a diagonal matrix. Here. What department are you in? What? Double E. Okay. But wait. No, wait a minute here. Have you never used MATLAB's diag
A long
thing?
time ago was the last time.
It was a long time ago.
Maybe.
Maybe? Okay.
Last year, I think.
Okay, last year. Okay, all right. Okay, that's fine. No. Just checking. I thought you were going to say math or something like that. Okay, so.
Last year, Winter, it was a CS class that has to use MATLAB for it.
Okay, all right. So it was in a CS class last year, which the memory of which do you even remember what class it was, or what was it?
220.
228. Okay. Okay, good. Figured. Okay. All right. So, okay, back to our thread here. So it's not over yet. You still have to show this is positive semi-definite. How do you show a matrix positive semi-definite? You simply show that the associated quadratic form is always non-negative. So you put a V on the left, V transpose V on the right. You plug that in here and see what happens, and you get this thing. And this turns out to be greater than or equal to 0 using the Cauchy-Schwarz inequality applied here. Okay? So, this is not obvious. Okay? This is not something that you just type in. This is like this is 30 minutes of thinking and breaking pencils and things like that. So. I just remembered something, speaking of that. I don't know that it's been announced yet, but it's just a suggestion. A suggestion actually is that it's not a bad thing to work on homework in possibly small groups of people, depending on who you are. People already probably have the sense to do this anyway, but you're being officially encouraged to work in small groups like that. So. In which case I could say it's after 30 minutes of working with breaking pencils, throwing pencils at the other people in the group and things like that. So, okay. So actually working in group is very good because it's easy to think you understand something. Very easy when you're by yourself. And it turns out if you have to address like 2 or 3 other people and try to explain it, actually even if, while you're explaining it, you'll realize so your mouth is going like this, right? And there'll be something in back of your head, I don't know what part of it is, will actually come out and say, just by the way, just looking at the others in the group, you'll realize this makes no sense whatsoever. What you're saying makes no sense. So it's a very good check. Whereas a lot of things by yourself can be totally obvious. Totally obvious. Then you try to explain it to someone. Also, if you try to explain it and this is long, complicated, you go like, look, super simple. It's so easy. You do this, all right? But then there's, hang on. I forgot to say this. And then also, by the way, you remember this, and then you put that there. And this is also a hint that this is way too complicated, your description of it. So anyway, so you're encouraged to work in small groups. Okay. All right. Let's move on. Okay. So geometric mean is concave. So this is the product of a bunch of variables. These have to be positive, although actually this works for non-negative. So it's a bunch of variables, and then the nth root of that. So that's concave, and it's the same type of argument as for log sum x, same type of thing. Okay. Some other connections, the idea of an epigraph and a sublevel set. So if you have any function, then the sublevel, the alpha sublevel set is the set of points with f value less than alpha. By the way, later in the course, f will be an objective or it will be some type of objective or something like that. And for example, if x is a design, then if f represents the power dissipated by some circuit design or something like this, this will be the set of designs that meet an alpha spec. That's what this is going to mean. Okay, so that's what a sublevel set will often mean. By the way, if it's an estimation problem and f is a measure of implausibility, like negative log likelihood in a statistical estimation problem, this will be the set of points which are at least alpha plausible values. Okay, so something like that. All right, now if you have a convex function, then the sublevel sets are convex. By the way, the converse of that is false, but it's a very important thing, and we'll have a name for it very soon, a function whose sublevel sets is convex. The real correct connection between convex function, convex set, because we've overloaded the word convex now to mean two things. It applies to sets and it applies to functions. The real connection is through something called the epigraph. So I guess epi means above. And so epigraph means everything above the graph. The graph of a function, of course, is the set of pairs x, y. So it's in Rn plus 1. It's the actual graph. The epigraph is everything above it. So if I have a function, the epigraph is this shaded region like this. And here's the real connection between convex sets and functions. A function is convex if and only if its epigraph is a convex set. So, and in fact, it turns out you should just be thinking about convex functions in terms of their epigraphs just always. So, for example, when I say here's a function like that, in fact, let's put a domain restriction on it from there to there, you should just immediately visualize this set drawn in, and it's a convex set. So actually, this is going to be important because we're going to do a lot of calculus with convex functions, and you want to think about what does it mean in terms of the sets. That's what you want to be doing. But so this you should just be thinking of at all times, the epigraph. Okay, let's look at Jensen's inequality. So our basic inequality for convexity is this. It says if you take a point between 0 and 1, if you take 2 points and take some kind of weighted average of the two, that's what this is, and evaluate it, so this says that f of the weighted average is less than the weighted average of f. I said it right. I always forget this. And I'll show you a mnemonic in a minute, which you can sneak off and do if you have something to draw on. You can even do it if you can't draw, but it takes me longer. Okay. Now, there's tons of extensions of this. For example, instead of just 2 points, you could have a finite number of points and a bunch of theta i's that add up to 1 and are non-negative. That's a convex combination. And the same inequality would be true. Then you could have a countably infinite number of points, some combination that way. And then you can have an infinite one. But the most general is this. If f is convex, then f of an expected value is less than or equal to the expected value of f of x. That's Jensen's inequality. And this is, this is where z is a random variable, however, which is in the domain of f almost surely. So that's this. And this is Jensen's inequality. And this basic case is nothing but this. It's a distribution on z, extremely simple. It takes only 2 values, x and y, with probability theta and 1 minus theta, and you recover this thing. So this is Jensen's inequality. I never remember Jensen's inequality, especially because whenever it comes up, usually f is like half the time convex, half concave. Of course, if it's concave, it goes the other way. And so I actually never remember it, and I usually have to just draw a picture and remember this thing. There's another way to say it, though. I know what that is. So if you want a general mnemonic about how it works, it basically says that for a convex function, dithering actually hurts. And let me explain what that means. It means that if I have a function, a point here, and here's a convex function, like that, okay? Let's imagine that's actually my target point in some process. But now, actually, when I manufacture it, I actually get a distribution of values like that, okay, whose mean is this point. Everybody Cool on this? So that's the, I mean, this happens, okay? So this is, and then this tells you the cost, okay? And this could be, you know, the power. I don't really care, something like that, or the speed of something. Let's make it the power, okay? So this is the power, and it basically says, you know, look, these points, that's where the manufacturing perturbations, they were on your side, right? The threshold voltage went up or whatever, something happened, and it actually dissipates less power than your nominal design. Everybody see that? And this is where it worked out badly. And now I ask, what's the expected value of the power? Well, what is it? Well, the first thing you would do is you'd say, well, look, it's around here, right? Because if I approximated this by, you know, an affine function, and I propagated this distribution through an affine function, then its mean would be the same. So the first quick answer is something like this, is, well, it's the same. If this is like, you know, 1 watt, then, and you have these manufacturing variations, you know, sometimes you're less than a watt, sometimes you're more. And it says that the average is going to be on the order of a watt, you know, like a watt. Everybody got that? But the fact is, it's worse, the average is worse than a watt. It's like, you know, 1.05. It can't be better. And the reason is this. It's true that when you go up and down here, you know, the first order approximation, in that case, you know, sometimes you're less than a watt, sometimes more. But because the curvature is upward, you get, let's see, you pay more when it's bad than you recover when it's good. Did that make any sense? And that's entirely due to the curvature. So that's my mnemonic for Jensen's inequality. It basically says manufacturing variation generally isn't good. So, yes?
What?
That's your question? Okay. So this is a good time for me to announce this. There will be periodically times, I'd say multiple times per lecture, where I'll go in something and it will make no sense whatsoever. It's best. I mean, if this starts happening like 3-4 times a lecture, then you can let me know. But that's good feedback. So it's best, at least for now, in the spirit of just rushing forward, we'll just move on. Did anyone understand what I said? Because a handful of people. They're probably just being polite. So, okay, that's all right. So you'll learn it to just move on. Okay, now, so let me this is a good point to kind of explain, give a signpost and say where we are and how this works. Here's what you're going to have to do is you're going to have to look at functions and figure out if they're convex or not. I mean, that's what you have to do. So the methods I just looked at involving, you know, lines and all that, if you have to resort to that, if you actually write out a Hessian, I mean, this is to be avoided, to be honest with you. This is not kind of this is sort of, you do this only at a last resort. Of course, every now and then you have to. We'll arrange that you will have to, because everyone should have to do this once or twice or something. But the point is, the right way to do it is using a convex calculus. And so the right way to do it is this. What's going to happen, this method 3, just general method, is going to work like this. You'll learn a bunch of atoms. You've already seen a bunch. Okay, affine functions, powers, log sum x, x squared over y, norms, you know, quadratic functions, things like that. Where once you know it, you know, minus log det x, you know it's convex. Okay. Then we're going to look at a calculus. And a calculus meaning methods to combine these and rules for showing it's convex. And you saw this with convex sets last lecture. But here it's going to be, there's going to be a bunch, there are going to be some simple ones here. Now, in this rule set, these divide into what I would call, you know, the sort of the really obvious basic ones. And then there's sort of that intermediate tier. And then you get into the advanced ones, and the ultra advanced ones, and things like that. There's sort of no limit on these things. So we'll start. I will tell you when we move into different levels of esoterica on this. But okay, so these are extremely basic. It says the following: if you have a convex function and you scale it by a non-negative scalar, it's convex. That's totally obvious. If you add 2 functions that are convex, it's convex. Okay, and that extends to adding 5 functions, and it goes to an integral or even an expected value of convex functions would be convex. Composition with an affine function. So if you precompose with an affine function, so in other words, if you apply an affine function, then a convex function, you get something that's convex. And it's many ways to check this. Actually, just directly is simple enough, just with the old theta in there. Okay, very simple to show these things. But let's look at some examples. We can make some examples now. F of x is minus log sum bi minus ai transpose x. And this, of course, is defined on the region where these are strictly positive. That's the interior of a polyhedron. So I have a polyhedron defined by ai transpose x less than bi. The interior is where that's strictly less, and that's where this makes sense. This is, by the way, called the log barrier for this polyhedron. And you have a minus sign here. So, that's kind of a very complicated, highly nonlinear function of x. You could work out the gradient, and you could work out the Hessian. This one wouldn't be too bad, because if you work out the Hessian, which I would not recommend doing by just getting there and slogging it out, calculating partial squared f partial squared xi xj, but using some of the rules for calculating Hessians. Some of these are in the appendix, by the way. It would work, but the easiest thing by far is to say this, here's my function. Ready? I'm going to apply, I'm going to take this function, which is phi of z is sum minus log zi. Okay, so that's it. It takes a bunch of variables, takes their logs, takes minus sum. Okay, that's a convex function. Why? Well, each of these is a convex function, and a sum is convex. That's a convex function. Again, there's nothing stunning yet. Now we're going to simply precompose this function with this affine mapping. I'll call it b minus ax. That's an affine mapping. Okay, and that gives you this function, and then here I just apply this composition rule. Okay, here's another one. Is the norm of any affine function. So norm ax plus b is going to be affine, convex. Sorry, it's going to be a convex function of x. Okay. Here's one that's maybe not totally obvious. So here's one convex function, and here's another one, like that. The pointwise maximum is this function here. It looks like that. Okay. So at each point, it's the maximum of the functions. Okay, it looks like that. By the way, in terms of epigraphs, what does this correspond to? Precisely. So calculating pointwise maximum of functions. In fact, you can even write some silly formula for it. Something like this: epi of max over I fi is equal to the intersection over I of epi fi, something like that. Okay, so that's the correspondence here. So that preserves convexity. Okay, and it means, for example, here this function, which is the max of a bunch of affine functions, has a piecewise linear function. That's convex. Obviously, not all piecewise linear functions are, but any piecewise linear function expressed this way is convex. Here's one. This is, again, not obvious. The sum of the r largest components of a vector. Okay? So take a vector in R50 and the sum of the top 3 elements. That's a very complicated piecewise linear function. It's convex. Okay? Why is it convex? Because it's the maximum of A transpose X, where A, this is for the sum of the top 3, is any vector with 3 1s and 47 zeros. Okay? Now there's a giant pile of those. Okay? There's 50 choose 3. But the point is, it's the maximum of 50 choose 3 linear functions. Done. It's convex. Okay? So you have to watch out here, because you slowly sneak up on this, and you'll find out after a while you've actually done something, and some of these things are not obvious. Proving this by another method would really could be very, very painful. Very painful. This one, the Hessian doesn't even exist. It's not even differentiable. So, which would save you the horrible trouble of getting in there by hand and working out a Hessian. But just proving that directly would be a real pain. Okay. Now this maximum business extends. and it extends to an infinite max or a pointwise supremum. So here's the statement. If you have a function of two variables, x and y, and suppose it's convex in x for each y in some set, don't even know what the set is, totally irrelevant what the set is. Finite, infinite, makes no difference whatsoever. Okay? Then it says that if you take the, again, you can read this as max if you haven't seen this before. This is simply, if you simply take the maximum over this possibly infinite collection of functions pointwise, you get a new function that's going to be convex. And here are some quick examples. Let's look at a couple of, let's start with this one. Let's take the maximum eigenvalue of a symmetric matrix. Now, we discussed that before. That is a really complicated function. For a matrix that is 6 by 6 or bigger, there is no formula for this. None. Because there's no formula for the roots of a 6th degree and order and higher order polynomial. Okay? I mean, you don't need to know that, but just it's a good thing to know. Well, it's not useful. It's just a cool thing to know. Okay? So okay. Now, so this is just, I mean, this is really a very complicated function, the maximum eigenvalue of a matrix. But watch this. It's the supremum of y transpose xy over all y that have, over the unit sphere. The unit sphere is the set of all points whose norm is 1. Now, let's check me and see how the argument goes. Look at y transpose xy. Now, by the way, when you look at that, you are, at this point, you are trained and wired. All the quadratic part of your brain should be lighting up. This has been proved in fMRI studies. Okay, good. So but the point is actually here, the variable is capital X. What kind of function of capital X is this? Remember, you have to suppress the flashing quadratic neurons. It's linear. That's a linear function of x. That's absolutely linear. This is sum xij, yi, yj. It's linear in x. Okay? So for each y, that's a linear function. This is a supremum of an infinite collection of linear functions. In fact, there's one for every point on the unit sphere in Rn. Okay? Supremum of a bunch of linear functions. Linear functions are convex. Supremum over these things is convex. That's a convex function. And now you know something that's not totally obvious. I mean, it's not that unobvious either, but it's, this would be, since that's like a 2-line proof or something like that, that's not bad. And of course, it's a disaster if you actually try to write out what lambda max is. I mean, just you write down square root of, no, that's not lambda max, but if you write down the largest of the lambda i's for which the characteristic polynomial vanishes, it's all over. You'll never recover. And so that's what this is. So this is an example. Okay, let me hit the next one. Is composition. So under certain circumstances, composition preserves convexity. So let's see what that is. If you have h of g of x, so the rule goes like this, so the famous one is this. It says that a convex increasing function of a convex function is convex. Okay? So if this thing will be convex, if you have a convex, if the outer function is convex and increasing, which I mean non-decreasing. Okay, so that's the condition. And the way to derive these as other ones, for example, it's convex if this thing is concave and h is convex and decreasing, roughly. That's what it is. Now, the way to check these is simply to write out the chain rule. So if you imagine that these functions are differentiable and of one variable, and you work out the second derivative and you get something like this. And from things like this is how you read off the rules. By the way, these things can, unless you're doing this all day long, these rules, you can easily forget them. what you should remember is there are composition rules, and you have to go back and find it. Whenever I'm somewhere and I have to figure this out, I actually quietly write this out and then figure out the rules myself. By the way, the rules hold even when these are non-differentiable. You don't need any derivatives. This is just to check. And let's actually, maybe we can make up a new rule. Let's make one up for fun. Ready? All right. Let's see. Let's try here. Let's say that G, I'm not going to remember what I'm saying, so I'm going to write it down. Suppose I told you, I have to get this right. Suppose I told you that G prime is positive. So G is going to be increasing. And I told you, do I even need G prime? No. Sorry. I take that back. I'm going to tell you that G is concave. So that means this here. And let's see if I can get it right. And let me ask, what are the conditions on H to make F concave? Does that make sense? So what we want is, we're going to say that we're going to assume that that's less than or equal to 0. And I need this thing to be less than or equal to 0. Well, that means this has to be positive. So I have to have H prime positive. So H has to be increasing. And then I look over here. That's positive no matter what. So I need this to be less than or equal to 0. And I just made up my very own new composition rule. And it's this. I hope I get this right. Okay, let me go very slowly. If H is concave and increasing, and G is concave. Okay, ready? So a concave increasing function of a concave function is concave. Did I say that right? Okay, so anyway, if I got it wrong, I don't care. You get the principle. Okay, it's a 300 level class. I can mess up minus signs all I like. That's your job to fix them and stuff like that. So I think I said that right. So, okay. So let's look at some examples. By the way, the only one I actually remember, to be honest with you, is a convex increasing function of a convex function is convex. Then I remember one other thing. There are composition rules. And then I have a note attached to that. There's lots of them, and they get very confusing. Although there are people I've noticed who just know them immediately. They'll say, "Oh yeah, no, that's a concave increasing function, decreasing function of a convex function. That's something or other." I'm like, really? I don't know. Then they have some internal mnemonics or something for doing this, but I don't know them. So just to tell you the truth, let's look at some examples. The exp of a convex function is convex. And that's, by the way, it's very interesting. It says that the exponential actually can only it preserves positive curvature. If a function curves up, xx also curves up. I mean, that's what it's saying geometrically. Inverse is interesting. It says the inverse of, but it's not the inverse. It's the reciprocal. There you go. That's the English word. The reciprocal of a positive concave function is convex. So, for example, let's see if I can get an example of that. 1 over the square root is that would be a convex function. And indeed it is. It's x to the minus 1/2, and it goes kind of like that. Sorry, for you, like that. Okay? So, actually, by the way, that's fine, because flipping the axis doesn't change the curvature property. So I don't have to draw it for you. If it looks convex for me, it looks convex for you. Okay. Okay. So that's the composition one. There are then vector composition ones, and I'll say, I'll give some examples here. So here you have vector composition. So here I have a function of a multi-argument function of a bunch of other functions. And now, of course, the possibilities just explode, because you have horrible things where you have a function that's sort of increasing in some components, decreasing in others. The arguments themselves are either convex, concave, and it gets very complicated. But here you'd have something like this. F is convex if all of the functions are convex, that's the easy case, and H is convex and decreasing in each argument. Non-decreasing, roughly speaking, increasing. By the way, there's one subtlety here that I want to point out. There's a tilde here. Tilde is the extended value extension. And I'm not going to spend time in lecture going over this, but you want to read that part of the book. at some point about this tilde, because that's not a typo. It's very important. Okay. And let me give a couple of examples here. By the way, what this shows is that actually the earlier rules that you learned are actually, they can be derived from this. Let me give you an example. How about the sum of convex functions? So here's a function h. H of z is 1 transpose z. It's the sum of the z's. Okay? This function is, well, let's work it out. It's obvious, it is certainly convex, right, in z. It's also increasing in each argument. You agree with that? Because it's just some zi. So it's obviously increasing in each argument. Therefore, by this composition rule, it says that if I compose this with a bunch of functions, each of which is convex, the result is convex. So from this rule, I've rederived the simpler rule, which is that a sum of convex functions is convex. Everybody see that? Let's try one more. Let's try h of z is the max of z. Well, the max function is itself convex. It's increasing in each argument. I mean, that's clear, right? If you increase any element of a vector, the max doesn't go down, so it's non-decreasing. Therefore, this subsumes actually several of the earlier ones. Actually, it turns out there's only 2 rules. There's this rule. In fact, there are only 2 rules. There's this rule, and there's the affine precomposition. But it's good for a human being, at least, to think of them as 8 or 10 rules or something. Quick question.
Increasing each argument, do you mean also that that they increase from vector to vector? Or just
No, nope, I do not mean that. Nope, I mean this. I mean hold all elements fixed except 1. Increase 1, the function cannot go down. That's what non-decreasing in each argument means. So, okay. So I think we'll quit here. This covers, these are the basic rules. By the way, this was very fast. Homework 2, we'll cement this. Don't worry. And we'll continue next time. And then maybe even by next week it'll get interesting.